All right, we're recording. Welcome back, everybody, to another TLC conversation. This time we're going to be talking with Lizzie Eardley. Did I pronounce that right, Lizzie?
Yeah, it's great.
Awesome. She's like, yeah, whatever, it's fine. Lizzie Eardley, now with Split, and she's a senior data scientist there, and she's going to be talking to us about chasing statistical ghosts when we're looking at our experimentation results. So first, let's introduce Lizzie, and then I'm going to hand the screen share over to her and let her do her presentation. So this is Lizzie, and I had the pleasure of getting to hear this talk at CXL live this year, and it was fantastic. I actually took more pictures of the screens during Lizzie's talk than just about anybody else's, and I was really excited when she agreed to come and share this with the rest of the TLC group. So you guys are in for a real treat. Lizzie has a background in astrophysics. She, used to study the stars and everything related to the math in cosmology, and then she, turned that around and started applying it to digital data, which I think is fantastic. So she's worked for Booking.com and Skyscanner, and now she's at Split as a senior data scientist, applying everything that she learned about cosmology and astronomy to digital data, which is really cool. And her focus now is inferring how humans respond to different product changes with online experimentation. She's based in Edinburgh. I'm terrible. Gosh.
Edinburgh?
Can I just say Scotland? And in her spare time, she likes to travel. And when it's not raining, and anybody who has spent any time in Scotland knows that there aren't very many of those days, she runs outside and tries to enjoy the Scottish countryside. So thanks so much, Lizzie. I really, really appreciate you taking the time to join us, and we're super excited to have you share your talk today. So I'm going to stop share, and I'm going to pass it over to you, and we will go from there. And as we make that pass, I'll just remind everybody what I've already reminded you a few times, but please do mute your lines during Lizzie's presentation here, and then feel free to unmute when she's done if you want to ask questions, or ask those questions over on the TLC Slack or in the Zoom chat. All right, take it away, Lizzie.
Great, thanks. Can everyone see my screen?
Yes, ma'am.
Excellent. So thanks very much to Kelly and the TLC team for inviting me. I think it's a good sign that anyone would want to hear the same talk twice. That's great. I hope I remembered enough to still be coherent the second time. There we go. So you already heard a bit about my background from Kelly. Thanks for the intro. So I used to be in astrophysics, and people are often surprised about how I made that switch, but it's actually very similar. So I used to analyze large data sets and make statistical inferences from those. And I still do very much the same kind of thing and apply the same kind of techniques now in online experimentation. And I've been really lucky to be exposed to some great experimentation companies. So Booking.com has a super impressive experimentation culture and platform, and Skyscanner, which I'm going to talk a bit more about throughout the talk. And as you heard, I'm currently working at Split. And so Split's a feature flagging and experimentation platform. And so I'm generally focusing on building out the A/B testing capabilities there and supporting customers in running good A/B tests. But this talk was actually put together whilst I was at Skyscanner. And so Skyscanner, if you don't know, is kind of a European version of Kayak, like Google Flights. So it's like a travel meta search engine. And it's actually a very mature experimentation company for its size. So it has its own in-house experimentation platform, and there'll be hundreds of online tests running concurrently at any given time across the app and the web. And so whilst I was at Skyscanner, as well as working on the platform itself, part of my role was in supporting colleagues in designing, running, and analyzing their A/B tests. So I saw hundreds of experiments coming through the system. And I started to notice the same common mistakes being made over and over again, and the same kind of common misinterpretations. So at Skyscanner, we started to call these statistical ghosts. And so by statistical ghost, what I mean is something which creeps into your analysis and makes you think that you have seen something, makes you think that you found something real, that you measured something, but the sad reality is there's nothing there at all. So it means you're being fooled by the data, and it's essentially all about those false positives. And so in this talk, I'm going to try and share some practical tips and guidelines to help you avoid those false positives or at least keep it down to the rate that you actually think that you're getting, and the one that you intend to get, rather than letting it get inflated by all these kind of common pitfalls. And so the reason why you want to avoid that inflated false positive rate is because it can be really costly to kind of devote time and resources and effort into iterating on a feature, or into releasing a feature which you think is having a positive impact, but really your time could be much better spent elsewhere, because you're actually just seeing a ghost and there's no real impact there at all. So these are the 4 ghosts that I'm going to talk about in this talk, and there are definitely plenty more kind of common pitfalls that you can make, but I think these are the 4 that come up most often, and they're also the 4 that have the biggest impact on your false positive rate. But before we get to those ghosts, I'm going to try and do a bit of a experimentation statistics reminder. So I'm sure a few of you on this talk already know this stuff, but I think like a refresher is useful in any case. And I should say at this point that all of this is based on frequentist statistics, so on frequentist fixed horizon hypothesis testing. So I'm not going to touch on any of the other experimentation frameworks here. In going through the stats, I think it's useful to have an example experiment in mind. So I picked a completely made up but potentially real experiment based on Skyscanner. So let's imagine that you work at Skyscanner, and say based on design input, you think that changing the Skyscanner logo is going to increase conversion. So here conversion could be the proportion of users who visit Skyscanner who end up making a booking, who end up booking a flight. So here you're going to change the logo in this test because you think that it's going to increase the conversion rate. But when we actually run an A/B test, when we formulate it into experimentation hypotheses, what we're actually testing is the null hypothesis. So that's the kind of the opposite. The null hypothesis is that changing the logo has no impact whatsoever. So it's a bit counterintuitive that when we run this test, it's because we think that we're going to increase the conversion rate. What we're actually testing is the null, and that's the idea that there's no impact at all. And the reason why it's set up this way is because there's an infinite number of ways that you could have some impact. So you could change conversion by 5%, by 10%, by minus 20%, but there's only that one exact scenario when you have 0 impact. So essentially when you run an A/B test, what you're doing is you're looking for evidence to reject that null hypothesis. And that is exactly where the p-value comes in. So here I put the kind of technical definition of p-value at the top there, but it's a bit of a mouthful, and I think not the most useful way of explaining it. So I've tried to explaining it in another way as well. So essentially a p-value is telling you how much evidence do you have to reject that null, or how likely is it that you would get the results that you just saw if that null were true. So again, using our Skyscanner experiment example, let's say that no one cares at all about changing the logo. The p-value is telling us how likely is it that we would have got this result anyway. And so when we're kind of talking about the null hypothesis, I think it's useful to think of AA tests, because an AA test is a situation where we know that that null hypothesis is true. So it's a case when we send all users, or users in A see the exact same version of our website as users in B. So there's no possible way that there could be a true impact. But even though in an AA test there's no true impact, we are still going to measure a range of observed impacts, just because of this noise and kind of natural variation. So even though there's no true impact, we'll still see a range of measured impacts. So here to try and explain the p-value a bit more, I've simulated 100,000 AA tests. So this is 100,000 simulations when there is no true impact, but we still see this range of measured impacts. And that's shown on the histogram there on the right. So you can see that out of these 100,000 AA tests, maybe 1 or 2 of those have a measured impact of, say, 8%. So what this means is that it's really, really unlikely that if there is no impact, that you would have seen a difference around 8%. So when you actually are running your test, if you get an 8% difference, you're going to get a very, very low p-value, because it's a super unlikely thing to get if that null were true. And this is, again, a different way to show those 100,000 simulated tests. So here it's the same data, but I plotted it cumulatively. So it's a bit weird because the y-axes are decreasing as you go up, but essentially this is showing you, of all of those 100,000 AA tests, how many of them had a measured difference at least as large as this value on the x-axis there. So you can kind of look at it. So at the 60% point on the y-axis, you can see that 60% of those tests had a measured difference of at least 1%. So most of them had at least 1% difference in conversion, and it's not that unlikely to measure a 1% difference. But what this means is that if you were to run your test and you measured a 1% difference in conversion, you would get a p-value of 0.6, because there's this exact mapping between the likelihood of getting it in an AA test and the p-value. So similarly, 20% of those AA tests had a difference of at least 3% in conversion, so we'd get a p-value of 0.2, because the p-value is just exactly saying how likely is it that you would have got this in an AA test. So this leads to something which I think is really interesting, characteristic of p-values, and that's that when that null is true, when there's no real difference, then every p-value is just as likely as any other. So it's uniformly distributed, and if you're running an AA test, you are essentially picking a random number between 0 and 1. So even though there's no true difference there, you are just as likely to get a p-value of 0.01 as you are to get a p-value of 0.99, saying they're all just as likely as each other. And so this is how we can use a simple p-value threshold to decide whether something is significant or not, and to fix our false positive rate. Because when that null is true, because it's uniformly distributed, we can already know how many p-values, or what are the chance of getting a p-value below that threshold compared to the chance above. So if we use a 0.05 threshold, then we know that 5% of all these AA tests are going to give us a p-value less than that. So 5% of those would look significant even though they're not, and that would be a 5% false positive rate. Okay, so back to the Skyscanner kind of mock experiment example. Let's say we set it up like this, and we measure 50% conversion in A, and then 53% conversion in B. So we've measured a 3% uplift in conversion. But if we put this into a statistical calculator, we'd get a p-value of 0.2. So again, what this means is that we would have 20% chance of seeing a 3% difference in conversion, even if nobody cared at all about the change in the logos. So that means it's not a particularly unlikely result to get. So we don't have much evidence to reject that null, and we can't really be confident that there is any true impact there. So it gives us basically not statistically significant result. And so this, I think, is a really important slide, because it's a mistake that people quite often make. So if you get a non-statistically significant result, this does not mean that your treatment had no impact. So people often see these words and they think, oh, that means there was no impact there at all, nobody cares about this change that I made. That's not what it means. So it means that you didn't have enough evidence to reject the null hypothesis, but that's not the same as rejecting the alternative hypothesis. So just because you didn't have enough evidence to confidently say that it did have an impact does not mean you're confident that it didn't have an impact. So I think the way that I would try and interpret non-statistically significant results is to think about the minimum likely detectable effect. So here, these are two kind of related experimentation terms, the power and the minimum likely detectable effect, or the MLDE. So the power is essentially telling you how likely is it that if an effect does exist, that you would be able to detect it in this experiment. And it depends on things like the sample size and how big that effect is. So you can see here I plotted a power curve for this example experiment, which we set up before with 1,000 users in each of A and B. So if there's no true difference in conversion, you have 5% chance of getting a significant result anyway, because that's just a false positive rate. But on the other hand, if you have a 10% difference in conversion, then you've got almost 100% chance. So you're pretty much guaranteed to see a significant result if there is that 10% difference. But anywhere in between, it's down to chance. So you're not guaranteed to get significance because it depends on noise. And the bigger the true difference is, the more likely you are to reach significance, but the smaller is the less likely. And so we usually kind of characterize this curve by one point, which is the minimum likely detectable effect. And likely is usually taken to be about 80%. So in interpreting not statistically significant results, I would usually say that means that I'm confident that there is not an impact larger than the minimum detectable effect, but you cannot say anything about any impacts smaller than the minimum detectable effect. Here, if we work out the power calculation for our example experiment, we can see the minimum detectable effect was 6%, 6.27%. So What this actually means is that changing the logo did not have an impact to conversion greater than about 6.27%, but it could have had a difference of 2%, 4%, 5%. We just didn't have enough power to be able to say anything about that. So that's why if you were to run this and see these non-statistically significant results, it would be really dangerous to conclude that it didn't have an impact, because you could be missing out on a 5% increase in conversion and really missing out on a great opportunity. Or if you were to go ahead and make the change anyway, you could actually be decreasing conversion by 5%. So it's really important to understand what your test is able to tell you and what you might be missing out on. And I think this is a very important part of the design of an experiment, which is often overlooked. And if you want to increase it, which you probably do if you're a Skyscanner, you care about 6% of conversion, then you need to increase the sample size. So maybe by running the experiment longer, or by running it on a larger audience. So you can see by increasing it from 1,000 to 100,000, the sample size, a minimum detectable effect goes from about 6% down to about 0.6%. So this is a much more useful experiment to run. And it means that we can make a much more valuable conclusion from a non-statistically significant result. But I always have get a lot of questions about how do you find the right minimum detectable effect. And it's a really hard question to answer, because there's no right answer. It depends. So if you want to be able to measure smaller impacts, you need to have a larger sample size, which means either you need to run your experiment longer, or you're exposing yourself to a bit more risk. So it's always a balance. And to work out what the right size for you is, you should ask yourself what size change you care about. So if you're Skyscanner, you definitely care about 6% change in conversion, but maybe you don't care about 0.01% change in conversion. So you need to know what matters for you. And you also need to know how much you realistically expect to change your metric. So if you don't expect your change in logo to change conversion by 10%, then there's not much point at all running an experiment if the minimum detectable effect is 10%. You essentially are just, if you don't have the power to detect an effect you expect, then you're never really going to learn much from that experiment. So you either need to test more dramatic changes, so you can increase that expected impact, or increase the traffic so you can reduce that minimum detectable effect. So just to conclude that stats section, the takeaways would be that the p-value is essentially just telling you how unlikely is it that you would see this difference that you measured if there were no impact. So if the null were true, is this data unlikely? And when there is no impact, every p-value is just as unlikely as any other. So people often think that when there's no impact, you're going to get a p-value of 1. That's not the case. If there's no impact, it's just a random number between 0 and 1. It's really important to do a power analysis and to be aware of your minimum detectable effect. And if you need to make your test more sensitive, then increase the sample size. And then finally, not statistically significant does not mean that your treatment had no impact. It just means that you weren't able to confidently say it did have an impact. So I would usually interpret that with regards to the minimum detectable effect, and to know what you can say and what you can't say, and what your test has actually been able to rule out. Okay, so that's the nitty-gritty stats section out the way, and now we can get on to the actual ghosts. And so remember, the ghosts are these common pitfalls which can lead you to have a much higher false positive rate than you expect. Okay, so the first ghost is the ghost of multiple comparisons. And this one is a tricky one to navigate, because I think when you're running an experiment, of course, you always want to learn as much as you possibly can. So it's very tempting to measure many different things, to look at different segments, and to try and really get those insights from the experiment. But as we saw before, every single p-value you look at brings you a fixed chance of a false positive. So if you're using p-value threshold 0.05, then look at one p-value and you'll get a 5% chance of having a false positive. But if you make any more comparisons, naturally you will get more false positives. And this applies to any kind of additional comparison. So it could be testing many metrics. So maybe you want to look at many different things for the same experiment, or testing multiple treatments. Maybe you want to test different variations. Or, and this is a really common one, if you look at different segments for the same experiment. So I see a lot of times people will run their test, they'll work at their false positive rate, they'll have one metric and one treatment, but then they'll look at how that change performed on different markets is a common one, different user segments. And they don't realize that even though that's one test, every single time you do that comparison, you have an additional chance of a false positive. And this can really stack up. So if we go back to the Skyscanner example, we had originally one treatment, one logo, and we had one metric, which is the conversion rate. So if we're using a 0.05 threshold, it gives us a 5% chance of a false positive. But on the other hand, let's imagine that the design team weren't sure which color of the logo would work best, and they asked you to test 8 different versions of this logo. Even though we're still only looking at one metric of conversion, and we're using our 5% thresholds, we're expecting a 5% false positive rate. By looking at 8 different versions of this, we're actually getting a 34% chance of a false positive. So that's such a huge increase, and it means that 1/3 of the time you're going to see a significant difference, even if nobody cares whatsoever about this logo. And I think this makes it really hard to work out when you do see a significant difference, whether it's a true impact or whether it's just one of those false positives. So of course, this increases the more comparisons you do, the higher the impact this has. So if we were to just look at the one logo, but then look at how it performed in 25 different markets, say, then we would have over 70% false positive rate. So we're pretty much always going to see a significant difference if we look at 25 different things. And that makes it near impossible to interpret whether you're actually measuring something real or whether you're just seeing a false positive due to this increased false positive rate due to this ghost. So as I said, this is a really tricky one, and it was a problem for us at Skyscanner. So this is an example of an old version of the Skyscanner experimentation scorecard. So every experiment that we ran at Skyscanner, we showed them a scorecard for these 12 metrics. And we always showed these 12 because even if an experiment wasn't targeting one of these particular metrics, we still definitely wanted to know if it was unintentionally having an impact on a different area or a different aspect of user behavior. So we wanted to give this holistic view of how the experiment was affecting all different kinds of user behavior. But having 12 metrics would actually have given us a 45% chance of a false positive. So we use the industry standard 5% threshold, and we expect a 5% false positive rate. But by showing 12 metrics, it actually means that almost half of all the experiments are going to show a significant difference. So even if all the experiments that ran at Skyscanner were complete rubbish, then almost half of them would look like they had a real impact on user behavior. So this is a huge problem because it really impacts the kind of trust in the platform and the ability of people to interpret what they're seeing. So the way that we tried to solve this was by introducing tiers to the metrics. So we set it up so that every time you set up your experiment, you had to register one key metric. So that would be the primary metric of interest, the metric which hopefully you would conclude on, and the metric which makes up your initial hypothesis. And then you would also be able to choose a handful of secondary metrics, which are metrics that perhaps are quite likely to be impacted or which are also key and you also want to pay attention to, but are not necessarily the main metric of the hypothesis. And then the way this helps is it allowed us to apply multiple comparison corrections. So I won't go into too much detail about the specific corrections, but we use these two here, and they both essentially work in the same way by taking into account how many comparisons you're making and adjusting that threshold that's used so it allows you to keep your false positive rate exactly where you want it to be. So it's a really useful way to look at many different things, but still stay in control of your error rate. And if you don't do that, and people often don't, then it can just be said that you are peeing on the research. So just to wrap up that ghost, to avoid the ghost of multiple comparisons, you should pre-register your metric of interest. So decide upfront what is the main metric that you are going to target, and then conclude your experiment on that metric. If you want to look at more things, if you want to look at more metrics or more user segments, then you should apply corrections, multiple comparison corrections, so that you are still in control of your false positive rate. Or if you see an unexpected outcome, maybe an unexpected segment performs differently, or a metric you didn't expect to move has a big difference, the safest thing to do is to rerun the experiment, but this time with that unexpected change as your primary metric. Okay, so the next ghost then. This ghost is the ghost of peaking. So peaking is a colloquial term for looking at an experiment whilst it's still running. So hopefully you would have done a power calculation and you've decided upfront how long your experiment should run for. And then peaking is when you look at the results before that time. So maybe you're curious, you want to see how it's doing, and you're checking the results. But the problem with this is that the standard experimentation statistics, so in our fixed horizon hypothesis testing, then our false positive rate only holds if we make one comparison at one predetermined point only. Doing anything else is always going to increase your false positive rate. So here, if you remember, we talked about the AA tests at the beginning. This is one of those simulated AA tests, and the p-value that we would have seen every day over a 30-day period. So again, it's an AA test, so there's no true impact there at all, but you can see that the p-value constantly fluctuates up and down anyway. And this is just due to noise. And the reason why peaking is a problem is because here, rather than one p-value, we're looking at 30 different p-values. And this means that we have many more chances just to happen on an instance where noise looks like a significant difference. So there's always going to be noise in the data, and we have a 5% chance of seeing noise which looks like a difference every time we look. And if we look multiple times, then we have much more chances to be fooled by this ghost and to think that we're seeing something real when it's just noise. So if you looked at this, you might think on day 4, 5, and 6 that it's definitely significant, there's definitely a real impact there, let's stop the experiment. But actually, if you let it run to the end, you'll see that the p-value ends way above the threshold because it was just normal noise and fluctuations at the beginning. So the problem actually only comes if you stop an experiment. So peaking is not a problem by itself, but the problem comes when you end an experiment early. And again, the more times you look, the bigger the impact to the false positive rate is. So let's say you ran a 3-week experiment and you looked at it every day. So you had 21 peaks. If you stop it as soon as it crosses that threshold, so as soon as it looks significant, then instead of a 5% false positive rate, we would have a 25% false positive rate. So this has a huge impact. I think people often underestimate how much impact this really has. But that's 5 times as much false positive rate just by peaking and looking every day. But I know there are definitely good practical business reasons to peak. So people, I often get a lot of pushback from this of why you can't just blindly follow the statistics and follow the rules. You might want to peak to check for bugs, to check that the experiment isn't completely tanking your metrics. And you probably want to peak and stop experiments early just to increase velocity, just to make sure you're not waiting unnecessarily when you've already seen something that's truly amazing. So there are reasons to peak, but there are also ways that you can peak safely. So if you look at the data, then don't stop an experiment unless you really, really have to. So maybe you want to stop it because it's completely tanked your metrics, because there's a bug, because it was set up incorrectly. That's fine. But if you do stop it, then you just can't conclude anything from the results that you got. So you're essentially invalidating the experiment if you stop it early. Unless, and this is another way to peak safely, unless you use non-standard statistical tests. So in this talk, I'm just talking about fixed horizon frequentist stats, but there are other statistical frameworks you can use which do let you peak safely. And I've added some links in the resources slide at the end if you want to read more about those. So this one's a simple one. To avoid this ghost, if you peak, just don't act on what you see. Don't stop that experiment early. Okay, so on to the third ghost then. So this one I've called bad metric wrong test. And this is all about measuring the right thing in the right way. And I think the importance of this one is quite often overlooked, but it can really change how useful your experiment is. So let's see. So these are the 4 things that I think make up a good experimentation metric. So a good metric to me is meaningful, it's interpretable, it's sensitive, and it's fit for the statistical test that you're going to apply to it. So I'm just going to go through them one by one. So a good metric is meaningful. And by meaningful, I mean that the metric is really capturing what you actually are trying to change. So it's measuring something that's really useful, really important to the business or to whatever you're trying to do. It has to actually capture what you're trying to change. So here is an example of not a very meaningful experimentation metric. It's a story maybe you've heard of. It's about a Chinese shoe company, and they released this Instagram advert. And so it has a fake hair over the image. And so the idea, I presume, is that people would see this ad, they see this image, they'd think they had a hair on their phone screen, and they'd try and swipe it away. And by swiping it, they would accidentally click through. So I'm going to guess that they had a pretty successful experimentation metric of click-through rate, right? But it actually, I believe, ended in them being banned from Instagram advertisement. And I imagine that it did not bring much useful, like valuable business to them, because it was just bringing people that did not intend to click on their ad. So they might have got a really amazing, significant result here, but that was not a meaningful metric, because all it's doing is tricking people into giving them a significant result. It's not actually bringing useful business value. So it's an example of gaming the system and not a meaningful metric. So a good metric is interpretable. And interpretable here, I mean, when the metric changes, you should be able to understand how customer behavior changed. How did your metric, or what did your change actually, how did it actually impact user behavior? And is this a good or bad thing? I think these are two really important things to be able to know as soon as you see that metric move. And this is an example of a non-interpretable metric, which often caused us problems at Skyscanner. So there was reasons why people wanted to measure this metric, for historical reasons and to match the business reporting, but it's not a very good and not a very interpretable experimentation metric. So that was the fraction of sessions that convert. So the number of converting sessions divided by the number of sessions. And the reason why this is not interpretable is because both the numerator and the denominator there can change. So maybe your experiment brings more people to the website, increases the number of sessions, or maybe it increases the number of conversions. And just because this metric moves, you don't necessarily know whether you move the denominator or the numerator. And you don't always know whether this was a good thing or a bad thing. So I used to hate this metric very much, because if it goes up, is that a good or bad? I don't know. It depends. So I think it's not interpretable, and it's definitely not a good primary metric for an experiment. So a good metric is sensitive. And this one is a tricky one because you can't always change the sensitivity, or you can't always pick a sensitive metric. So some metrics are just not inherently sensitive, for example, revenue or retention, but they're nonetheless really important for a business to measure. So ideally your metric will be sensitive, but if it's not inherently sensitive, there are some ways to improve the sensitivity. For example, using some variance reduction techniques, or you can use some outlier removal techniques. But the ideal metric is one where you can detect those small changes. And then finally, a good metric is fit for the test. So this one, I think, is something that people get wrong quite often, but is super important. So when I say fit for the test, what I mean is that the metric satisfies all the assumptions of the statistical test that you're going to apply to it. So the most common statistical tests, like the t-test and the chi-squared test, will assume these two things. They'll assume that the observations that you're going to put into it, so the data you're putting in, is independent. And they assume that the error or the noise in the data is normally distributed. And I think people often know about that second one, and they worry about the second one. But if you have a large enough sample size, that's usually fine. But it's actually the first one, this independent observations, that I see catch people out most often. And it can really have a huge impact on your false positive rate. So as an example of non-independent observations, at Skyscanner, we would allocate users into A or B. So each user, if they come to the site twice, they'll be in the same treatment group. But if we were to measure something like a session conversion rate, then that would be not independent observations, and it would not fit these standard tests. So anything like conversions per session, conversions per search, maybe click-through rate, every time you see an ad, do you click on it? All these things are not independent observations. And the reason why it's a problem is because what happens in a user's second session is probably correlated to what happens in a user's first session. So our estimates of the variance are going to be wrong. We're going to underestimate the variance, and then we're going to have a higher false positive rate than we expect. So this is a sneaky one, and it's something which people often get wrong and can really increase the false positive rate. So just to recap that one, a good metric is meaningful, it's interpretable, it's sensitive, and it satisfies all the assumptions of the statistical test that will apply to it. And then this is the last ghost I'm talking about today. It's the ghost of almost significance. So this one is a bit of a pet peeve. I think it's the ghost of temptation is something that people do very often. It comes up all the time and drives me crazy. So it's basically it's when people say that something is almost significant, because there is just no such thing as almost significant. So we saw before that our p-values are uniformly distributed. So when the null is true, when there's no effect, then every p-value is just as likely as any other. So when we set our threshold in the beginning, we know what the false positive rate is. And if you think that something that's just above the threshold is significant, you are just naturally increasing that false positive rate yourself by thinking that. And you're also introducing a bias there. So I've never heard anyone say that the p-value just below the threshold is almost not significant. So this is why it's a complete bias, and it's I understand why, because people want to see that significant result, but it just means that you are asking to be fooled by this ghost. So please don't drive your data scientists crazy. Never say these words. There's no such thing as almost significant. There's no such thing as nearly significant or trending towards significance or barely significant. It just either is significant or it isn't. So to avoid this ghost, just follow these simple guidelines. If the p-value is less than your threshold, then great, you can act as if that data is not noise, and you can make your interpretations and make your conclusions. But if the p-value is above the threshold, even if it's only slightly above, the only thing you can safely do is to remain uncertain and act as if that data is noise. So those were the 4 ghosts. I'll just recap them one by one. So we met the ghost of multiple comparisons. So to avoid this one, decide up front what your key metric is. If you're going to look at more things, whether it's more metrics, more treatments, or more segments, apply corrections so that you can stay in control of your false positive rate. And if you see something unexpected, then rerun the test. Then we met the ghost of peaking. Simply, if you do look at the data, just don't act on it. Don't stop that experiment early. And then we talked about bad metric, wrong test. So try and pick a metric which is meaningful, which is interpretable, which is sensitive, and make sure that it fits all the assumptions of the test that you're going to apply to it. And lastly, there's no such thing as almost significance. If your p-value is below the threshold, great. If it's above, then just remain uncertain and act as if that data is noise. And that's it. Here's some links if you want to read more about any of the stuff covered there. Thanks very much. I hope it's useful.
Awesome. Thanks, Lizzie. We're having a great conversation over here on the call channel. Dylan grabbed a shot of your almost significant ghost here. So I think maybe we need to put that in somebody needs to make a little dancing icon of it so that we can all use it. Don't do that. For those of you who are asking on, I've got 2 different people that have already asked on the Zoom chat. Yes, you will get a copy of this deck. And of course, you also have the recording, but I want you to be able to click on the links in this resource tab. Lizzie, thank you for providing. Let me scroll up here because I've got some good questions coming through. First one, if you reach stat sig with an effect size that's smaller than your MDE, do you just ignore the result if you assumed a fixed sample size?
No, I would not. So this is actually something I have debated recently. So the MDE is useful for, primarily useful for like a power analysis at the beginning in helping you set your sample size. And if you have something which is significant but less than your MDE, it just means that you might have missed this. If this is the true impact, you might have missed it if you ran it again, but you still saw a significant result. So I would still interpret that as significant and take that as a meaningful result.
Okay. Multiple comparisons. Okay, so if your metrics normally, like outside of a test, if they are connected to each other, if they have some sort of compounding effect on each other, can you still use, if they're correlated with each other, do you have to worry about the multiple comparisons? Do you still have to make a correction for those?
Yes, so yes, you should make a correction, but it's much more difficult if they're correlated. So That's one of the reasons why we use two different types of multiple comparison corrections as Skyscanner. So the kind of easiest one to implement is the Bonferroni correction.
Right,
But
but that would double it if you had two, right?
yeah, so if there is any correlation between the two metrics, then that's going to be a very conservative correction. So you would actually reduce your false positive rate too much, and it would be too strict. So that's why we use the Benjamin-Hofberg correction as well. So in that case, it still doesn't necessarily make it perfect, but it's a much less strict one in that if there are these correlations, because it looks at the ranks rather than the exact values, then it's a better one to use if there's correlations between the metrics.
Awesome. Corey asks, if you find a bug that has affected the experiment while you were peaking, obviously you're going to stop it and you're going to fix it, but then the follow-up to that is, once you fixed it, do you relaunch it? And when you relaunch it, do you need to do anything to, exclude people who had been in it before, any kind of corrections to make sure that, what happened before doesn't affect your newly relaunched experiment?
Yeah, that's a tricky one. I think that depends on the kind of nature of the traffic that you have. So ideally, yeah, you would be able to exclude those, but then sometimes excluding those users can introduce a bias in itself. So maybe by excluding users that saw your experiment last week, you're excluding the kind of frequent visitors. So it's a bit of a tricky one, and you probably need to think about what is going to have the least bias. Yeah, if you have constantly new traffic, then that's great. If you think that people might be affected by seeing the previous one, you could either split only the control group into the new A and B and then reduce your traffic, so you don't, or you can re-randomize, I think. So if you're concerned that people saw a bug would not come back, as long as you re-randomize the groups, then you should be okay.
Gotcha. All right, guys, back to the TLC group. You guys have any additional questions we haven't asked yet? Now's your chance. I see Matt typing, but he's probably answering questions rather than asking them. By the way, he was excited to see another Edinburgh alum, apparently. Yeah. You both graduated there. Anyone else? Got any burning questions that you want to ask? I can't tell you how often we get people saying, wait, I don't understand. How does looking at the test affect my error rate? And you explained it lovely. It's just the likelihood that you'll see it over time. If every time you look at it, the error rate is, or the chance of seeing it is this percent, and the more you look at it, the higher your chances of seeing it. And to be clear, typically, I posted over there, like in my experience, it's not one per day. So your examples were actually quite conservative. You have multiple people and they're looking, especially like in the first few days that you launch the test, right? You've got like 15 people all checking, and they're checking multiple times a day. So the chances that they get a false positive are sky high.
Yep. And people never stop it early because it isn't significant.
Right. What about, one of the other questions that we get a lot is in a situation where you've calculated your minimal detectable effect, and you've looked at your historical results, you've looked at the thing that you're changing, and you've decided, okay, it's maybe because of the cost of the thing that you're going to implement if it wins, or the cost of like a new tool or whatever, that you have to have a 5% lift. So this is very clearly your MDE. You've also said that you're only willing to accept a 5% chance of a false positive, so you're going to set your confidence at 95%. You don't know anything about power because nobody ever talks about it. So you've gone into your tools calculator and you've put the information in there, and it says you need to run it for 2 weeks, 3 weeks, whatever. And you get to 3 weeks and you're close. And we're not going to say approaching, but you're close to that level that you need to see. Obviously, what we all hear all the time is, well, how much longer would I need to run the test to get to statistical significance? Can you explain what you're violating when you make that choice to extend the test?
Yeah, so one of my slides said that the statistics of frequentist fixed horizon hypothesis testing are only valid if you make one comparison at one predetermined time. So as soon as you kind of let it run a little bit longer, you are both making multiple comparisons, but you're also doing that bias in that if it was significant, you would have stopped it already. So you are changing your experiment design based on what you're seeing. So had you decided originally to run it for longer, that would be fine. But actually what you've done is completed that test and got a non-significant result. So you've already got your result by that point, but then you are essentially trying to running another one in a sense, but you're adding that bias because you've already got a very close result.
Right. So I have two new questions over here that I'm about to ask, but I want to ask the flip of the one I just asked, because the opposite thing that happens is you said it had to be a 5% lift. You calculated it. You needed to run it for 2 weeks. At week 1 or day 3, your lift is significantly higher than the minimum that you had said you needed to see in order to make a decision. What is the harm in stopping early?
This would be peaking, yeah. So, so the harm is that you have a much higher false positive rate. So maybe you're seeing this lift now, and you might think you're going to be 95% confident that this is a true lift, but it's because you're peaking, because you're giving yourself many more chances to see a false positive, you are no longer keeping that 5% false positive rate.
So even though the tool tells you 95%, the fact that you looked early, that 95% may not be accurate.
Yeah, and this is kind of a problem with a lot of the online tools, I think, is that they leave a lot of flexibility and kind of trust in the hands of the user, which has its benefits, but you do need to understand how to use it correctly and resist that temptation to see what you want to see. So they give you a lot of information, but they also trust you to use that safely and wisely, which is difficult, I think.
If you don't have a data scientist on your team that's slapping your hand and say, don't do that.
Yes.
Okay, so let's flip over to Matt's question. Any thoughts on why you control for bias in type 1 error control? Wait, it's updating, sorry. Won't there be bias in treatment effects under sequential tests, especially under early stopping rules?
So it depends what kind of sequential test you're doing, but there are some where early stopping is fine. So there are different ways to set it up, but there are some that are, I think the main benefit of using them is that early stopping is okay. So they would take into account either how many times you have peaked or will peak, and they will spread that error essentially so that you can still be confident if you stop it early that you are still controlling your error rate. I'm not sure about the bias part, what that was referring to.
Matt says, which test, first of all, can you point out which tests control for magnitude bias? He's not asking about type 1 error rate, but bias in the magnitude of the treatment effect.
Yeah, so that's a tough one. I actually don't know a very particular kind of test. I think some way that I've seen it before is when people hold out a control group, so that it's not part of the original test, but you would rerun it afterwards. So the magnitude bias comes from, although at least the way I'm interpreting it, you're more likely to have a significant result when it is slightly higher. So you're slightly likely to overestimate the true effect of all the experiments you're running because you stop them when they're above that threshold. So I think the way that I've seen it kind of approached before is when people have a holdout group that is not part of the original experiment, and then they retest those significant results, and then you kind of avoid that bias because it's not the data that made you make that decision, but it's a fresh new data set.
Okay, so I think what Matt is actually talking about with early stopping, there's the bias effect because you're only going to early stop if you see a huge lift, and then you're biasing your results towards only things that are huge lifts, and so you're only going to early stop in that scenario. But he says, yes, you got it, by the way. Let me ask Merritt's question. I know of at least one high test volume company that peaks a lot, does not test a sample size, but imposes a stable trend standard, like sustained increase or diverging trend over many days, to any effects before considering them significant. Is there any grounding for this type of approach in stats land? So to clarify, I know what company he's talking about, but the idea is even if you get statistical significance on day one, they're not going to stop the test, but they're going to start looking for a consistent or diverging trend in, say, its conversion rate for the two recipes over a certain period of time or certain number of days or whatever before so they're applying an additional standard to mitigate the impact of peaking. Is that...
Are they essentially allowing experimenters to peak? So they are saying you can stop early, but as long as it looks stable?
That's right. But in other words, they're saying, yes, if you get to 95% significance or 99 or whatever their standards are, but it can't just be one data point. It's got to be multiple data points over, I can't remember if it's 3 or 5 days. And by the way, the trend in the actual conversion rates need to be parallel or diverging over that time frame before you can call it.
Okay. I don't know too much about it. I guess I would question if you've already got a stable trend, then it sounds like you probably haven't got that much noise left. So you've probably already got a big enough sample size to reach significance. So it sounds a bit, I wonder if it's a subjective decision of whether it's a stable trend or whether it's actually a quantitative one. And if it is a quantitative one, I guess it depends very much on how they've set it up. But I would wonder if it probably either lets you have a higher false positive rate but less false negatives, or vice versa. So it depends. It's not something I have seen. Depends how they set it up.
Interesting. It's probably not founded in statistics, but maybe not overly dangerous. At least as dangerous as making an early decision based on one data point.
Yeah, it's better.
Basically, they're making an early decision based on a family of data points, which I'm not sure that really controls for your false positive. It may compound it, actually.
Yeah, I might ask.
We have to do some simulations and see what it looks like. Never really thought about it that way. We've got about 3 more minutes. If anybody has any additional questions, go. Oh, wait, Corey does. That does mean you need a fairly large amount of traffic if you also want to control your runtime, though. Corey, I'm not sure what that was related to. I'm sorry, I just noticed it. But if you have more information, add it. In the meantime, everyone else, just a reminder that our next talk 2 or 3 weeks, I think, from now, is with Els and Justine, and they're going to talk about asking better questions for qualitative research and testing so that we can feed that into experimentation. Corey added extra information. If you want to control your runtime, the use of a holdout cell to get, using a holdout cell to get separate data sets means you need a fairly large amount of traffic if you also want to control for runtime.
Yes, for sure. Is one of the many things in experimentation which is easier if you have a huge traffic size. Everything becomes a lot easier once you've got a huge traffic size.
Yep. Zoom question for you really quick. You said earlier when we were talking about power that the way that you impact or you increase power is through traffic. Isn't it also true that you can increase power through effect size with smaller amounts of traffic?
Yes, so if you have a larger effect size, you'll be more likely to be able to detect it, so you will naturally have higher power. So yes, that's why if you are struggling to get enough power to detect anything, if you make bigger changes, so maybe if you combine 2 different changes that you expect to have a bigger impact, that would give you more power without needing to increase the sample size.
Okay, so the 2 ways to affect power are more traffic or bigger changes.
Yes, you can also use different metrics. Different metrics will have different power. If you have like a 50% conversion rate, you have much higher power than if you have, say, a 1% base conversion rate.
Good point. 3 ways.
Yeah.
All right. Anybody have any additional questions for Lizzie? All right. Thank you so much, Lizzie. I really, really appreciate you sharing. Just as enjoyable the second time around.
Thanks very much.
All right, everybody. I will save the recording, put it on YouTube, and post it on the TLC Slack and send an email out with the deck as well. Thanks, everybody. Have a great weekend.